Pre-calculus notes 2.5, day 1. So we're going to be looking at polynomials, and we have the fundamental theorem of algebra here that says if f of x is a polynomial of degree n, where n is greater than 0, then f has to have at least one 0 in the complex number system. And remember that the complex number system is composed of both real and imaginary. So the complex numbers have just plain real numbers within them. And so that just says, if it's of degree 3, we have at least one 0 in the complex number system. No matter what the degree is, as long as it's greater than 0, there are complex solutions. So in part A here, example 1, a first degree polynomial f of x equals x minus 4. Well, that exponent right there is to the first. It's x to the first. So that's greater than 0. So we have at least one 0 and the 0 for that, right? 0 equals x minus 4. Solve for it. X is 4. That 0 is 4. So it has exactly one 0. In part B, counting multiplicity, the second degree polynomial function has two zeros, which are, and so on this one, if we just go ahead and set it equal to 0. Oh, actually, I have the wrong, oh, yeah, this is okay. So x minus 2, but this happens to be a perfect square trinomial, so it factors into x minus 2 squared. So the x equaling 2 is the 0, but since it has an exponent of 2, x equals 2 is of multiplicity 2. And so the second degree polynomial has two zeros if you include multiplicity. So each power is counting as a multiplicity. So it's a multiplicity 2, therefore we're counting for both of the zeros. So x equals 2 of multiplicity 2. In part C, the third degree, finding the zeros. So 0 is equal to, factor that, and we'll have an x squared plus 9. And so either x is 0 or x squared plus 9 is 0. And so 0 is one of them, and x squared plus 9, if I solve, I get a negative 9. So I take the square root of both sides, and I get plus or minus the square root of negative 9, which is 3i. So x equals plus or minus 3i. So the three zeros are going to be x equals 0 and plus or minus 3i. And we expect that because it's of degree 3. Rational zero test. If this polynomial has integer coefficients, then every rational zero has this form of p over q, where p is a factor of the constant term. So this number right here is your p in factors of that number. And then q is a factor of the leading coefficient. So q is something that is a factor of that leading coefficient. And what this does, this rational zero test or theorem, is it's going to allow me to figure out how to factor polynomials that are of a higher degree than 2. When they're higher than a degree of 2 and they don't factor nicely, like in example 1 part C, we can have problems trying to find the zeros. And so this rational zero test is going to help us out. And so list all the possible rational zeros for this function. Well, what I'm going to do, first of all, this doesn't have integer coefficients. So I am going to write it out equal to 0 because I'm going to try and find the zeros, the places where this polynomial would cross the x-axis. And I'm going to multiply both sides by 9. So I'm going to multiply the left by 9, and I'm going to multiply the right by 9. Since it's an equation, I can do that. And then that's going to clear out those fractions. And now I have a polynomial where I have integer coefficients, and the rational zero theorem or test will work. And so a naught is 4. And so my possible rational zeros, my P over Q. I'm going to just put a fraction bar here. Factors of this constant C, 4, are 1, 2, and 4. Over factors of the leading coefficient, that A sub n is 9. And factors of 9 are 1, 3, and 9. And something to, on all of these, the possible rational roots are positive or negative. And so if I take all the possibilities, I have to take each factor of 4, the 1, the 2, and the 4, and put them over the 1, the 3, and the 9. So 1 goes over 1 and makes 1. 1 goes over 3 and makes 1/3. 1 goes over 9 and makes 1/9. Then I have to do the same thing with 2. 2 over 1 is 2. 2 over 3 is going to be a 2/3. And 2 over 9 is a 2/9. And same thing with 4. 4 over 1 is 4. 4 over 3 is 4/3. And 4 over 9 is 4/9. And you need plus or minus. And that is the list of all possible rational zeros for this polynomial. So what we're going to do is we are going to use the list of possible rational zeros to help break down and factor a quantity. And so in f of x, in this next example, example 3, I'm looking at trying to find where is it equal to 0. It happens to already have integer coefficients, so the rational root theorem applies. And so my P over Q, plus or minus again, factors of 3, which are just 1 and 3, over factors of 4, which are 1, 2, and 4. And so my list of possible rational roots, which this needs to be shown on all of these, is 1 over each of them, 1 over 1, 1 over 2, and 1 over 4. 1 over 1 is 1. You have a 1/2 and a 1/4. And then 3 over each of those. So 3 over 1 is 3, 3 over 2, and then 3 over 4. So those are the list of possible rational roots. So what we're going to do is use synthetic division and just start with one of these and try to get a reduced polynomial. And I'll talk about what I mean by that when we get there. But we're going to go ahead and divide f of x. We're really dividing by the factor x minus 1, but the root or 0 then would be 1. And so we've got 4, 8, 1, and -3. And all descending powers are there, 3, 2, 1 to the 0th. Remember that with synthetic division, every power must be represented. We bring down the 4, multiply times 1, add, multiply 12 by 1, add, multiply 13 by 1, get 13. And this would be my remainder. And since that remainder is not 0, 1 is not a root, and x minus 1 is not a factor. So I got to keep on going until I get down to something that gives me a remainder 0. So it's a little bit of trial and error. It is what it is. But we're trying to get where we have a remainder of 0. And we're going to keep on trying these rational roots. And I like to start with, try the 1 and maybe the 3, then maybe go back to the 1/2. Work with ones that are easier to start with. So bring down the 4, multiply by -1. Add, we have 4, multiply by -1. Add, multiply by -1, we have 3. Oh, that's nice. We got 0. That means when I divide by x plus 1 is a factor because we have a remainder of 0. -1 is a root, so that's one of my zeros. And this right here gives me the coefficients of a polynomial that is of 1 degree less than we started with. So we started with an x cubed. So these are the coefficients of a polynomial of degree 2. So this represents 4x squared plus 4x minus 3. And so that says that if I factor f of x, or actually I'm going to try and find the zeros, so I'm going to rewrite this if I can get this to erase. I'm going to set that equal to 0. And one of the factors is x plus 1. And when I divide by x plus 1, I get 4x squared plus 4x minus 3 is that quotient. And the nice thing now is we have different techniques for a quadratic. We don't have to keep on going with the rational roots and synthetic division until I find them all, because when it gets down to a quadratic, I can factor it. I can use the quadratic formula. I have options. And this one will factor. And it factors 2x minus 1 and 2x plus 3. That gives me a 6 minus, or not, yeah, a 6 minus 2 is 4, so that's good. And so then my zeros, or my roots, are -1, 1/2, and -3/2. And notice the 1/2 and the -3/2 were in our list for possible rational zeros. So you list all of the possible rational zeros, and then you just start with synthetic division, and the goal is to get one where you have a remainder of 0, and then you've got that reduced polynomial that you can either keep if it's still of higher degree than 2, where you can't just use things that we know in terms of factoring or the quadratic formula, then you keep on using synthetic division on that until you can get it reduced further. All right. So on example 5 here, if I have this equal to 0, notice we have integer coefficients. So find all real solutions. So we're still talking about the rational roots, so you are in this section, you need to show the possible factors of p over q, and p is 14, so it's 1, 2, 7, and 14 in the numerator. Oh, you know what? I didn't change this. We don't want that to be a 4 out there. We're just going to it's going to be a 1x cubed, so change that problem. Sorry about that. Make that just a 1. And so anyway, so factors of 14 are going to be 1, 2, 7, and 14. And then factors of 1 are just 1. Change the problem. Not a 4x cubed, just a 1x cubed. And so my possible rational roots, don't forget plus or minus, is just 1. Each of these over 1 are just going to be those lists of numbers. So those are my possible rational roots. And so if I start, doing the trial and error with synthetic division, well, 1 didn't work. I tried -1. I get 17. So that's, and I can keep on going. But it says I can use a graphing utility to narrow down the choices. Let's go to Desmos. And I don't need the next one. So we've got x cubed. Let's see. So x cubed. X cubed. Shoot, I didn't figure out how to do this in advance. Let's see. So x cubed. I'm looking for something to, sorry about that. I'm looking for a caret symbol and I don't seem to have that. So x function stats miscellaneous. Okay, well, I'm going to do this x times x squared just because I don't know where the caret button is right offhand. I just didn't pre-practice that, sorry. Minus 7x squared. And then minus 11x and plus 14. All right, so I cheated and used x times x squared for x cubed because, yeah, the caret did somewhere there, but I don't know where. So anyway, so there's that. And so we've got it cubed. And as I'm looking at it, so hopefully I've got all of that there. I am just looking at where is this crossing. And notice that it looks at -2. If I touch that there, -2 comma 0, that looks like -2 is a root. That's what we're talking about. These other ones, I mean, you can kind of guess it's before 1 and slightly after 8, so those might not even be rational roots. They could be irrational, but we have one rational at -2. And so now that I can see that, then I know to go back to that list of possible rational roots and choose -2. So that was one of my possibilities. And so now I'm expecting this to work out. And I used the graph to kind of narrow it down. When there's a lot of possible rational roots, it's kind of a nice thing to do. So bring down the 1, multiply, add, we have a positive 18, 7, and multiply, and oh, we got there. And so these are the coefficients of the reduced polynomials. So right now, I can say that this factors into x plus 2. If -2 is the root, x plus 2 is the factor. And then the 1, -9, and 7 are the coefficients of a polynomial of 1 degree less, which is a quadratic. And so then to solve for where this is 0, we've got that x is -2 is one of them, but this x squared minus 9x plus 7 does not factor. And when it doesn't factor, that means it didn't give me rational roots. They're irrational. So I need to use the quadratic equation. And we're just going to approximate these so we don't get down to that. That's 53 underneath the radical. So my exact solutions are x is -2 or this 9 plus or minus the square root of 53 over 2, or x is -2, and then put those into your calculator and you're going to get an 8.14 to 2 decimal places and a 0.86. And so to 2 decimals, those would be my answers. Again, you get those by taking 9 plus the square root of 53 over 2, and 9 minus the square root of 53 over 2. And so this one would give you the 0.86, and the sum would give you the 8.14 if you plug those in. But yeah, using the possible rational roots to then try to whittle it down to a remainder of 0 so you can have the coefficients of a reduced polynomial, and it can just help you out in factoring and finding zeros.